Hello, and welcome to another edition of Groups Without Algebra. I'm Josh, and I'll be leading this video today. So today I want to talk about the finite simple group of order 2. So this is a finite group with exactly 2 elements, and it can be shown using algebra or otherwise that this is it. There's only one. So every other group that you could think of, or any kind of group you could think of with exactly 2 elements in it, is isomorphic to the finite simple group of order 2. So I'll kind of show some examples of what that looks like and kind of give some justification as to why that's the case, starting with these tiles here representing the symmetric group. So let's start with the symmetric group. So what is a symmetric group of finite elements? That's basically the group of permutations on those elements. So if you have n elements, then you'll have n factorial permutations. So in the case of 2, 2 factorial equals 2. So there's 2 elements in the group. Because generally speaking, the symmetric group on n elements, or n elements, has order n factorial. So here we have 2 things, and we have a group of order 2. So what would that look like? Well, let's take a look at these 2 tiles and think about the permutations of them. So if you think of an ordering as going from, first and second, so here is one permutation, and then here's another permutation, first and second, and that's it. There's only 2. So this is a representation of the symmetric group of order 2, basically permuting these 2 distinct tiles. So let's then talk about cyclic groups. So if you remember from a previous video, we talked about cyclic groups, and that's related to the number of rotations. You can think of a cycle graph or a regular polygon, and the number of times if you rotate that you'll get that number of elements. So it's kind of symmetry related to rotations. So here's a tile, and this has, again, you can kind of think of it as a polygon with 2 points, which of course doesn't really exist. Maybe it's a line, maybe it's not, but we can kind of definitely think of rotations of this tile. So here's one configuration with the white and black, and if I rotate it, I get another configuration, black and white, and if I rotate it again 180 degrees, I go back to the same thing. So this looks like a group, has 2 elements, this configuration and this configuration. I can cycle through the elements using rotations, 180 degrees, for example. So this is a nice representation of a cyclic group of order 2. The last kind of group I want to talk about for finite groups is a dihedral group. So the dihedral group is the number of reflections on a regular polygon that maintain symmetry. So you can kind of think of that as like turning over a square. So as, for example, going back to kind of a previous tile, a square has 1, 2, 3, 4 ways you can kind of flip it to maintain symmetry. And so if we go back to our imaginary two-sided polygon, which is ridiculous, but this tile exists, so let's use this. So how can we orient this to maintain the same symmetry? We can rotate it like this to maintain the symmetry, but we get a different configuration. And we can rotate it like this, or kind of flip it or reflect it, I should say, to maintain symmetry as well. So this is the dihedral group of order 2. And this is, again, like other groups of order 2, this is isomorphic to the finite simple group of order 2. I hope you enjoyed this, and I hope you've enjoyed Groups Without Algebra.